All right, it's Adam again, here with another exciting episode of epidemiology and biostatistics. Today, we're going to go over Lecture 5. This will be Challenges in Statistics, as if we haven't had enough already. Some of the objectives we'll cover today include understanding basic concepts of multiple comparisons and how they can be problematic when dealing with our statistics. We want to determine when correction is needed for multiple comparisons, delineate some of the traps that multiple comparisons can lay out for us, and they'll talk a little bit about normality of data, defining Gaussian distributions as an ideal, apply some of those concepts of testing for normality to data, and then determining distribution type. We'll also look at defining outliers and understand their impact on a data set, and then understand the concept of robust statistics. And again, we always want to get rid of our outliers. Not really, we like to include them because otherwise our data could be biased. First thing we'll talk about today is our multiple comparisons concepts. So the issue with multiple comparisons is when you're making two independent comparisons, what is our chance that one or both will result in a statistically significant conclusion just by chance alone? So we know that frequently our alpha level is set at 0.05, which means that 1 in 20 is an acceptable type 1 error rate for us. So again, that's a type 1 error of finding a statistically significant difference or rejecting the null hypothesis when no difference actually exists. So again, we know that the first will not be significant probably about 95% of the time, right? And then if you start to look at your chances that the second one will not be significant, which is by itself also 0.95, when you combine those two chances together, you get around 10%. So now we've kind of doubled our chances of finding a statistically significant difference when one has really not existed in the first place. Right, so you can generalize that logic to more comparisons, and essentially, if you look at this k number of independent variables or number of comparisons you're going to be making, you'll find that as you can plug it into this 0.95 raised to the k power, that as you increase your value of k, that chance of getting a statistically significant result when one is not actually present will increase. And so if you make lots of comparisons, you're more likely to find statistically significant results just by chance. This is a good slide showing you that the number of comparisons will have a direct effect on the number of significant results that you're going to get. As you have the comparisons you're making on the x-axis and the number of significant results you'll get on the y-axis on the left side here, you'll see that the number definitely increases pretty significantly to the point where you're almost getting all significant results by just doing a number of, a very large number of comparisons. So we'll see some of the ways that we can kind of prevent this from occurring, and some of the ways that we can help get around the multiple comparisons problem. So when making multiple comparisons, you'll see that each one individually, if you don't have any kind of corrections made for multiple comparisons, will traditionally have that 0.05% significance level, meaning that as long as the p-value is less than 0.05, you would consider to be significant. This would be a per comparison error rate, so every single comparison would have that 0.05 level. Basically, as you increase that number of comparisons you're making, as you saw in the slide previous, that the chance of making that type 1 error or finding a statistically significant difference when none actually exists becomes larger. So again, bigger chances for type 1 error as you make more comparisons. What we can do to help prevent that is use this idea of a family-wise error rate. So again, if you were to take these multiple comparisons and redo the significance level so that that significance level applies to all of the comparisons that you're making, meaning that instead of each one being set at 5%, you can change that value and make it so that the individual comparisons are more difficult to achieve significance because you're making that p-value lower, or that alpha level lower for each one, but in that way the entire grouping together in total has a 5% chance of showing that sort of difference by chance alone. So one of the ways that we can adjust our alpha level for these multiple comparisons for this family-wise error rate is to do some corrections. And so one of the most common ones you're going to see is this Bonferroni correction. So after unveiling his dish at Olive Garden, he decided to make this correction for family-wise error rates with multiple comparisons. And so essentially what you're just doing is that you're going to divide your p-value, that 0.05, by the number of comparisons you're going to make. And so that way you now have a new alpha level for each of those comparisons to achieve. So for instance, if you were to do 20 different comparisons for your study, and again, if you were to look at that previous graph, you'll see that that would have roughly a 65% chance of obtaining one or more statistically significant results. Well, using the Bonferroni correction, you can basically just take that 0.05 and divide it by 20. And so now you have this new alpha level of 0.0025, meaning each of those comparisons would have to achieve a p-value of less than 0.0025 in order to be statistically significant. Now, what this does is it makes it more difficult to make a type 1 error because your p-value or your alpha level is going to be much lower. But on the other hand, that will increase your risk for making a type 2 error, meaning that there is a true difference between the groups or between whatever comparison you're making. It's going to be more difficult to find it. So this is going to be one of those things where having a larger sample size is going to be able to help give you more power to determine those differences if they truly exist. So let's look at some of the traps of multiple comparisons. One thing that we can look at is this idea of data torture, basically analyzing data without a plan. Whenever you are performing an experiment or a study, you really should try to have as many of these points, these comparisons, and all these ideas kind of pre-thought out beforehand, because otherwise you really run into the risk of introducing bias into your study. So say, for instance, there's the idea of data torture that can occur when investigators, without a clear plan, can analyze their data in many different ways. So for instance, if you had your statistician goes, oh, okay, so I see you already have calculated the p-value, and the surgeon goes, yes, I use multinomial logistic regression. The statistician says, really? Oh, how'd you come up with that idea? How'd you decide to perform that sort of test? And so the surgeon says, well, I was running SPSS, which is the statistical package for the social sciences. It's basically one of the go-to programs that you can use on your computer to do statistics for you. But he said, okay, well, I basically tried each of the different analyses in the drop-down menu until I found one that gave me the smallest p-value. Obviously, this is not a very good idea because just by doing all these different comparisons without really having a plan and just finding the one that is most convenient isn't really good science. You really should have a good idea of what type of comparisons, what type of statistical tests you're going to be doing beforehand, instead of just cherry picking the right ones that give you the results that you like. Another good example of this would be former Washington Mayor Marion Barry said, well, you know, outside of killings, Washington has one of the lowest crime rates in the country. Yes, that is true. If you were to take out the killings, that's one of the lowest, but you can't really just cherry pick and say what type of stats you want to look at and which ones you don't. So there's lots of different ways to wring out statistical significance from the data. So for instance, you can look at doing things like changing the definition of your outcomes. So instead of looking at, say, all-cause mortality, you're going to look at cardiovascular mortality. Instead of looking at your outcome of being, say, change in LDL cholesterol, you're going to all of a sudden start to look at change in triglycerides. You could do things like changing your inclusion or exclusion criteria partway through the study to try to get better patients that might be more representative of the results that you're looking for. Removing outliers arbitrarily. We kind of talked about this before when we talked about censored entries in those survival curves we saw. Perhaps even clumping or separating groups differently. A good example of this would be gerrymandering, which is pretty germane to the election that will be going on here pretty soon. And then also just trying out different statistical tests until you find the one that actually massages the data into something that looks good to you. So, and again, eventually, if you keep testing, something will emerge as statistically significant from any kind of reasonably complicated data set. So, as you increase that number of comparisons to nearly infinite, you're going to find something that works, something that achieves statistical significance. So this is something we definitely want to avoid whenever you're doing research, and this is something you should be wary of whenever you're reading research of other people. Here is a really good video that discusses gerrymandering. It's pretty short, only about 3.5 minutes, and I will let you kind of play that on your own so you can check that out. But it's definitely a very interesting way of changing the lines of where voters live in order to give you the results that you want in an election. There's also this idea of publication bias, and this is something that is kind of endemic to the scientific literature nowadays. It's kind of a big problem. And so one of the things that we see whenever you're trying to publish data is that the editors prefer to publish papers that report statistically significant results. It's not super exciting when you publish data that says, oh, we didn't find any difference. We couldn't reject the null hypothesis. Even though that may be a very important finding, especially if it is in conflict with other things that did show statistical significance, it's just not all that interesting to read in a journal. So those are much less likely to either be submitted for publication or to actually be published in the first place. So if you can imagine, the chance of observing a significant result in a published study could be much greater than 5% because, again, if you're only cherry picking and taking things that show statistical significance, if they were not using the proper procedures, they could definitely have some bias there in kind of picking out things that show differences when really nothing existed in the first place, or more type 1 errors. And for example, there's a study done in 2008 where basically they're trying to look at the industry-sponsored investigations on the efficacy of antidepressant drugs. So these would be the drug companies themselves funding these research, funding this research. And so they were looking at papers between 1987 to 2004. The FDA, or Food and Drug Administration, was reviewing 74 such studies and categorized them as either being positive, negative, or questionable results. And what they found is that they had 38 studies that were positive, and 37 of those were published. Well, that was pretty good, right? When you were looking at the ones that were negative or questionable, 36 of those fell into that category. 22 were not published. 11 were not published, or 11 were published with a spin, meaning that they were kind of showing the data in a better light than probably the actual numbers showed. And then 3 of the negative studies were published with clear negative findings. So really, even though the data is there to say that maybe the efficacy of these drugs are not quite what we think it is, really the only thing you're really going to be reading is going to be the positive results. So it's definite publication bias towards showing positive results or showing statistical significance, even if it's truly not there. Here's a very recent video by John Oliver, kind of talking about scientific studies and some of this publication bias. I would suggest you watch it on your own time if you like. It's a little bit longer, about 20 minutes or so, and does contain some adult language. So I will not be testing you on this, but if you would like to watch, I will leave you to it. So looking at multiple time points or doing sequential analyses is another way that we can potentially have these multiple comparisons issues. So to properly interpret the p-value, the experimental protocol really must be set in advance. So that includes the population that you're going to look at, including inclusion, exclusion criteria, the sample size you're going to use, including using your power calculations, the data collection methods, results analysis. All that really needs to be set a priori, or before the start of the actual data collection. And so it's tempting to run the experiment more times in sequence in order to find the results that you're looking for to reach statistical significance. You really shouldn't be doing this approach because really the results at that point are invalid. The experiment should not continue when the result, or the experiment in this case would be continue when the result is not significant and stops when it finally does reach significance. So again, not the most rigorous statistical methods being used here. Really, if you say we're going to look for, a year's worth of patients during this time frame, and if you don't find the results you want, say, okay, well, we'll try another year and see what we get there. That's really kind of invalid ways of researching the data. You can also have multiple subgroups. So by analyzing multiple subgroups of data is a form of generating multiple comparisons issues. So say, for instance, you're looking at heart disease in a mock study, and you have 2 randomized groups that are given the same treatment. And then within that group, you identify 6 subgroups. Well, let's say we had the sickest subjects in treatment B had a statistically significant improvement in survival with the p-value less than 0.025. So again, that would be statistically significant if our alpha is at 0.05. And looking at this, if you were to look at all the different comparisons they're making, the chance of obtaining a statistically significant result with that number of comparisons is 26%, even if all the null hypotheses are true. And again, here we see that they're randomized on a mock trial, so they're getting the same exact treatment. There really shouldn't be any significant results based on the null hypothesis being 100% true in this case. But if all the subgroup comparisons are defined in advance, it is possible to correct for these multiple comparisons. So, for instance, doing your Bonferroni correction, or if you are able to show that the subgroup analysis is in line with the actual overall analysis, sometimes that gives you a little bit more credence to saying that these results are consistent. One of the other issues that can come up when looking at multiple comparisons traps is looking at the idea of disease clusters. So say, for instance, you have a school, a particular school that developed, 5 children developed leukemia last year. Now, it's easy for humans because we're really kind of trained to look for patterns. We're trained to look for clusters of things. So is this a potential exposure that they all shared that led to this leukemia? Is there a particular coincidence that could have led to this? And so you may ask yourself, well, what is the probability that 5 children in this particular school would all get leukemia this particular year? And so based on leukemia rates, you could potentially calculate that, but that's not really what we're looking for. It's not going to really tell us the information we want. The better question to ask would be, what is the probability that 5 children in any school would develop the same severe disease in the same year? So again, this is better because it's going to require that we're looking at the definition of the population in the schools that we're looking at, the time span you'd like to define, and then the severity of the diseases. And so very frequently, say 1,000 clusters are reported each year, we realize that about 3/4 of them are not really clusters in the first case and are really not investigated. And the other quarter are generally found to be coincidences after further investigation. So chance alone can cause a cluster. It's just that humans are designed to look for patterns even when none really exist. So looking at multiple predictions being a potential issue here. So let's say, for instance, in the year 2000, Intergovernmental Panel on Climate Change, we're making predictions about future climate changes. And so, they were wondering, well, how accurate were those predictions over the next 7 years? And so they actually found that answering that question was pretty much impossible because the report contained a lot of predictions and didn't really specify which sources of climate data should be used. And so because they weren't really being specific about it beforehand, those predictions weren't all that useful. You can really only evaluate the accuracy of those predictions or diagnosis when it's defined precisely, including the timing, methodology, and the data sources. So again, just not having a plan beforehand can lead to lots of issues where the results are going to be more ambiguous or pretty much not useful in the most part. You also have issues where you're combining groups, and so in the case where you're comparing two groups, the two groups really must be defined as part of the study design. If the groups are being defined by the data, or you're defining patients after the data has already been collected, it's easy to make lots of different comparisons kind of implicitly, and then in which case the results cannot be interpreted. So that's why it's really important to make sure that the randomization procedure is done correctly, to make sure that patients are being included or excluded according to very strict criteria that doesn't change over time. Because again, that's going to skew your data and introduce bias into the results. So moving on, we're next going to be talking about normal distributions and trying to determine whether the stuff we're looking at, the data we're looking at, is Gaussian or not. So we said that many statistical tests assume that the data that you're sampling from it comes from a Gaussian distribution, or that normal distribution. Again, remember that bell curve that we were looking at. And so when looking at an ideal Gaussian distribution, you would see that it really should be including very, very low negative numbers, super high positive numbers. But we realize that in typical patients, if we're looking at biology, there's a lot of limitations to those extremes, whether it be physiologic, physical, biologic, whatever happens to be. Human people tend to, revert back to the mean. And so we kind of lack a lot of those extreme values. If you imagine looking at blood pressure, you're going to see a lot of values kind of regress back to 120/80, but it'd be very rare that you'd find a patient who has, say a blood pressure of 20/10, because they'd probably be dead at that point, or pretty close to it. So why use tests that rely on this Gaussian distribution? Well, the tests are useful when the data is sampled from a distribution that at least approximates a Gaussian distribution. So what does Gaussian distributions really look like if you're actually taking a randomized sample from a normally distributed population? So the next figure is going to show some of that simulated data, and you'll see that each distribution shows a group of values that were randomly chosen from a Gaussian distribution. And you'll notice that you really don't see that bell curve unless the sample sizes are very, very large. Otherwise, the distribution tends to look less symmetrical. So as you can see here, these were all random samples taken from the same data subset. Again, looking back at that body temperature example we were talking about. And if you take just random samples of an N of 12, you can see that even though this all pulls from a randomly distributed set of data or a Gaussian distribution, it really doesn't look all that too bell curved. However, if you were to increase your sample size, you start to see the bell curve start to appear a little bit more. So with the N of 130, it appears to be a little bit more bell curvish, but is a little less symmetrical than what you would see with a true Gaussian distribution. So just be aware that, just by looking at it with your eyes alone is not enough to determine whether the data is going to be normally distributed. Just another example of how some of these Gaussian distributions don't always look Gaussian. You see the data points kind of showing the spread of the data around the mean. So how can we test to see if a distribution is normally, or if a sample is taken from a normal distribution or not? You can do tests for normality. And so basically these are statistical tests that can be used to quantify how much a data set deviates from the expectations of a Gaussian distribution, otherwise called normality test. So the first step you want to do is to quantify how far a set of values that you have differs from the predictions of a Gaussian distribution. Now, of course, there's lots of complex tests that do this and lots of complex names, but the key thing to look at is to look at the p-values that are generated from this. So when a normality test computes a p-value, it answers the following question, that if you were to randomly sample from a Gaussian population, what is the probability of obtaining a sample that deviates from a Gaussian distribution as much or more so than your sample does? So what are the probability or what are the chances that the results that you have or the samples that you took would deviate that much from a Gaussian distribution? So if you were to have a high p-value that results from these normality tests, essentially you're saying that the null hypothesis is that the data are sampled from a normal Gaussian population, there's no differences between them. And so if the p-value is very large, you're going to see that this is basically, even though I've said not inconsistent, we already talked about how we have a lot of double negatives we're talking about in statistics. Basically what this says is that you cannot reject the null hypothesis and that the data that you have is representative of that Gaussian distribution. So you kind of pass the normality test. So again, we're checking for that deviation from the Gaussian ideal, and if you have a high p-values, means that it's pretty close to that true ideal. Now, the test does not show that the population that you pulled from itself was actually Gaussian. It's just saying that the data set that you have, how much it deviates from a true Gaussian ideal. And again, the power of these normality tests is going to increase with your sample size. So the more people you have, the closer you should be able to get to a true Gaussian distribution, the more power you have to show that. If you have a small p-value, though, what you're going to be showing here is that your sample deviates enough from a Gaussian distribution to show that it is not normally distributed, meaning that it is, deviates too far away from that. So again, if you had a p-value from these normality tests that was less than 0.05, you have to reject the null hypothesis and show that your sample is not taken from a Gaussian population. So what could it mean when your data fails a normality test? So again, you'd be having a small p-value here. It is possible that you may be able to find a different type of distribution for your data. So it could be a log normal data, which means that your data looks more Gaussian once you plot it on a logarithmic scale. So that could be one possibility. The other thing would be is that you could have the presence of one or a few outliers that could be causing the normality test to fail. So at which point we'll run an outlier test, which we'll talk about in just a minute. If the deviation is pretty small, you may not need to do anything. Otherwise, you may need to switch over to non-parametric tests that don't assume a Gaussian distribution. So this is a pretty key point when determining whether a statistical test is going to be appropriate for the data that you're looking at. So basically what we have here is that for normal distributions or for Gaussian distributions, you can use what we call parametric tests. In a couple lectures from now, we're going to talk about what those tests are, but just know that parametric tests are going to be for normal distributions, and that we have non-parametric tests for non-normal distributions. So non and non go together. And essentially what we're going to be showing when we look at this is that because non-normally distributed data kind of differs so much from that Gaussian ideal, that the non-parametric tests are going to be considered to be more robust. Or when you're using a non-parametric test, it's more difficult to achieve a statistically significant result, meaning that your chance of making a type 1 error is lower, making the results more robust. Because when you find a truly significant difference, you can be pretty sure that that's a true result and not just a false positive. So looking at outliers next. We can see that outliers occur for several different reasons. So it could be that you have an invalid data entry, could just be due to normal biological diversity, random chance. Sometimes you can have experimental mistakes, or you could have wrong assumptions being made. Again, if you had a Gaussian distribution versus a log normal. So a good example for this is if, say for instance, when I was talking about my coral snake study, one of the things that we would do is actually go through poison center cases that had been entered by the specialist working at the poison center. And so if we were, say, monitoring blood pressure entries for those patients, it's pretty easy for someone to actually mistype something and say, oh, they had a blood pressure of 12 over 80 instead of 120 over 80. And that could be an outlier, but you'd have to kind of go back and investigate if that truly was an outlier or if there was something else going on there. So identifying outliers can be pretty challenging. It really should not be done informally. You really need to do outlier tests to determine whether a data point you have is truly an outlier or not. And again, humans have a tendency to see too many and tend to be biased in that. So even though it looks like an outlier, it may not be, and you can't just eyeball it and determine that. So again, looking here, you can see even though that there's pretty wide scatter, and you can see definitely what looks like some outliers there, all of these data sets were taken and sampled from a Gaussian distribution, right? So because we can't eyeball this, we typically have to have tests that let us know whether or not these values are truly outliers. So a question you would ask yourself before using an outlier test is, was there a mistake made in the data entry? Is the outlier really a code for missing values? Sometimes you'll see that where a value will be listed as 0 or 1 or something like that as a code if it's a missing value. Was there a problem noticed during the experiment? Could the extreme values be a result of biological variability? And is it possible the distribution is not Gaussian? So again, you'd probably want to run a normality test before trying to run one of these outlier tests. So doing these outlier tests, basically having answered no to all the previous questions, the two possibilities really remain that one, the extreme values of the came from the same distribution as the other values and should not be treated specially. So it's just one of the natural values that would come up just due to random chance. Or the other thing you can see is the extreme value was a result of a mistake, so you could either correct or remove it. I think it's important when you're reporting out on data like this that you're explicit about this and let them know that, hey, some of these data were either removed or corrected based on mistakes. The more transparent you can be and the more transparent authors are, the better off you can be and more kind of more credence you can take in their claims. And then an outlier test can answer the question is that if the values that you had were sampled from a Gaussian distribution, what is the chance that you would find one value as far from the others as you observed? So in this case, if you came back, ran an outlier test and had a low p-value, so saying less than 0.05, that would say basically the outlier is not from the same distribution. It's a very low possibility that just due to random chance you would have a value that extreme, in which case you would reject the null hypothesis that the data is sampled from a Gaussian distribution. And so at that point you say, okay, well, this is not normally distributed data, and we should be using non-parametric tests. On the other hand, if you have a high p-value, it's showing that there's no evidence that extreme value that you got is coming from a different distribution than the rest. So basically, you cannot reject the null hypothesis and just assume that the data is all sampled from a Gaussian distribution. So here you can see an example of data that looks like you had some pretty significant outliers, but really was just on a log normal distribution. You can see here on the right side after it's being corrected for that how it assumes that normal Gaussian distribution. So, and again, going back to the concept of robust statistics, again, rather than eliminating outliers, some statistical methods are designed so that the outliers will have little effect. If you go back to one of our first lectures, we talked about that typically when you're looking at the mean value of something, outliers can influence it pretty significantly. So, means are very sensitive to outliers, whereas we talked about the median simply by it being the middle value or the 50th percentile, we say that is much less likely to be affected by outliers. So essentially, by using methods of data analysis that are not very affected by outliers, they're considered to be more robust. They're more difficult to achieve statistical significance, but they are also less likely to make a type 1 error. And so the simplest robust statistic is the median. And obviously we know that the median is going to be more robust than the mean is not because the median is less affected by those outliers. Okay, so now I'll do a little Q&A. So the first question is, does it make sense to ask whether a particular data set is Gaussian? Not really. The common misconception is to think that normality tests are asking whether a particular set of data is Gaussian, but really what we're looking for there is to see whether or not the data that we're looking at appears to be sampled from a Gaussian distribution. So a little difference there. Gaussian is referring to the entire population itself, and when you were sampling from that, you're pulling a random sample from that Gaussian distribution. You perform those normality tests to make sure that the data you have still represents that Gaussian distribution. Is it legitimate to remove outliers? Some people may see it as cheating, but really should not be just done on an ad hoc basis because, again, if you do not have very explicit criteria for why you exclude data, it can be seen as introducing bias and can invalidate your results. You really should have established rules and methods for removing data because otherwise, again, that can call your whole question or your results into question at that point. And then what does it mean to remove or eliminate an outlier? Basically, they are eliminated from the analyses that are performed and at the value as if it was never collected. You can still graph them, but they should be clearly marked. And then by removing an outlier from the analysis, it doesn't mean that you should completely, remove that value from your data collection, but really should be excluded and then recorded and then be able to be reported on in your results. How should outlier removals be reported? As I mentioned, scientific papers really should be stating how many values were removed as outliers, and then what criteria were used to identify them, and whether those criteria were chosen as part of the experimental design. Because really, this should all be decisions that are made before the study is even done. You can also, you'll sometimes see papers that will do the calculations with and without the outliers just to make sure that the inclusion of those outliers did not skew your results and show something completely different. That way you can have a little bit more, take a little bit more credence in the results that the researchers are showing you. So anywho, that's it for this fifth lecture. If you guys have any questions, please email me and I'll get back to you guys. Thanks and see you soon.